after we've seen how to encode with Lempel Welch, we now want to decode, the decompress step. And in principle, it's easy. We have to reverse what the encoder has done. Otherwise, we don't get back to the same source text. The details are a little more tricky because, as we'll see, the decoding is always a bit lagging behind. And the intuition behind that is easy. Remember, we always encode one code word and then store a new one. And so we have to do the same in the decoder. So the normal mode of operation is we decode a substring from the source text, which we find as a fixed length code word. So the splitting of the coded text into code words is easy. It's always, in the example, the slide said 12 bits is a typical size. In fact, it's a parameter you can often play with if you use zip programs. So there's a fixed length code word, so it's always clear what the next code word is in the coded text. And hopefully that maps to something in your dictionary, so you can decode that code word to something in the clear text, in the source text. And after we've done that, we have to add a new string to the dictionary, because that's what the encoder did, and we have to keep adding these because they might be used in the future. And just for notation, I'll always use y for the thing that we decoded, and then x with c added as the thing that we add to the dictionary. And now the trick is that in the encoder, x and y was y and x was basically the same. But now, because we're lagging one step behind, x is the previously decoded thing, right? Remember, we can only store the new thing to the dictionary once we know what it is. The encoder encoded one step and then added that thing to the dictionary. In the decoder, I can't really do that. I first have to decode the thing before I can add it. And so the easiest way to deal with that is to say we decode one thing and then add something, but what we add is actually the previous string. So we'll have x as the phrase that we decoded in the last step, y the phrase that we decode now, and xc, this one more letter that we should add, is actually the first character of y, because that's the new phrase. So here's a concrete example that may make it more clear why we have to do it this complicated way. In the previous case, in the previous step, we decoded x, and that was ban. Now, the encoder would have added ban plus the next letter to the dictionary. But at the point of decoding ban, we don't know what a is. We don't know what the next letter is. We haven't seen that a yet. So we have to wait for the next step. When we decode y, which is an in this case, then we know the first letter of y was an a. And only then can we add xc to the dictionary. Okay? That's the complication. We're always lagging one step behind because we need this first letter of the new phrase. So we can also only start adding after we've seen two phrases decoded. We can't start earlier. Clear so far? Let's have an example for that as well. Similar setup, but a different string so that it doesn't get too boring. So what we get is a sequence of code words. Now these are written in gray. They will come up highlighted later on. We start again with filling the dictionary with all the single characters in our alphabet. That's the same as before, and it's important we use the same initial state, of course. And then you see the code words are just these numbers. They're really fixed length bit strings. I just wrote them in decimal to make it more human friendly. But you should think of these of all having, say, 12 bits. And there's leading zeros where the numbers are shorter. Is that clear? That was a question that came up on Campus Wire, so I thought I'd point this out again. All right. So how does the decoding work? We see a number, 67. And so we find the entry in the dictionary. That's the first phrase that we decode. That's great. And so here's it's written as a table, but it's producing the source code and what you add to the dictionary in one go. Just to have it nicely written up. So we decode this to C. That's the first part of the source text, and you will be able to read the source text down from here at the end. We can't do anything else. We should add C and the next character to the dictionary, but we can't do that yet. So we move on to the second code word, decode what that is. It's again a single character, so we read that from the dictionary. We find the A, and now we add a new phrase to the dictionary, namely the previous phrase plus the first character of the current phrase. So that's Y. Sorry, no, that's A. That's the new phrase. X is the previous phrase. That's C. And so we add X and the first character of Y to the dictionary. And that's what we do. Okay? And again, of course, we don't really store this as string. We can store it as one code word plus one letter. Uses less space. Okay, keep going like this for a while. So 78 is another single character letter. So we decode that. And now we have another round of a previous phrase, A, a new phrase, N. So we add AN to the dictionary as shown here. Now in these simple examples at the beginning, X and Y are single characters. But in the general case, X is any string, and what we add to X is the first character of Y. One more, we decode the space, and we add previous phrase plus first character to the dictionary. One more, and then things first get more interesting. So we have the 129. That's one of the phrases we added. So it decodes to AN. It's the first time we use one of these. So let me write one last time. Our previous phrase was the B. The new phrase is AN. So the first letter of AN is A, which means we add BA to the dictionary. And that's what you see here. All right. So just to the point where we see, OK, we have understood things. Now suddenly we run into this weird situation. The next coded word is the 133, which would be the next code to fill. But we haven't filled it yet. So we don't know what to do. We don't know what to decode it to. And it looks like this is a terrible dead end, which comes from the fact that the encoding is always one step ahead. And now in decoding, we never quite catch up. And so we can run into this situation. Fortunately, by just looking at this a bit more closely, we can resolve it. So again, problem comes from this lagging behind. And that might lead to the situation that we want to decode the code word that we're just about to fill after this round. So what can we do? We can have a close look at when exactly this situation can happen. And then you'll see that it's actually not a problem. So we're decoding the same phrase that we're now filling. And that means in the encoder also generated that phrase right from the previous step. It has to be like that. Because otherwise the encoder would also not have had that phrase. So the encoder started with AN and encoded that, and then added to the dictionary ANA. And then ANA comes again. That's exactly the situation. It can only happen like this. The encoder has a phrase, adds a new character, and then that new phrase directly appears one more time. But if that happens, we know that this AN is the same as this AN, and this A here is the same as this A here. So we actually know a lot more about this specific string. And in particular, we know that this C must be the first character of the previous phrase in this case. All right, so again, follow along the picture. We have AN in the encoder previously. We encode that, but then we add the A and put that into the dictionary as a new phrase. And now it says the situation means we've now used that phrase as the next step. So the next phrase must be A and A. And that's the next thing that the encoder encodes. So it uses this new phrase. And that means that this A and A is the same as this A and A. So the blue A always is the first character of X. So with this special case of just using the case analysis and substituting that here it's not the first character of Y, but simply the first character of X again, we can resolve that case. So here's the code for that. It looks like a lot of text, but apart from this special case, there's nothing really complicated going on. We start with a dictionary. In this case, we don't need a fancy trie or any special data structure. It's just an array with strings or pairs of previous phrase and one character. And we initialize the first section with all the single characters in the alphabet. Then we have, as before, a variable for the next free code word. As a shorthand, we cache the next code word to decode. And Y is this phrase that we're now decoding. Same name as before. And we have the source text. Initially, that's just the first phrase, and we'll keep adding to it. Now we iterate through the length of the coded text. We remember the previous phrase in X. What was Y last time is X now. We look at the next code word. And then if that code word is the special case, we're trying to use the code word that we're just about to write to the dictionary. Then we know Y is of this special form. We know what to do. And otherwise, it's one that we added earlier, so we can look it up from the dictionary. Then we add that to our source text, store the new phrase. So this is the real Y that we decoded. So this is that's the phrase that we add to the next point, and it captures both cases now because we set Y here to this and advance this. I think the code is not too complicated after you've seen the special case. The rest is exactly as in the example coded down. So to finish off our example from before, if we're in this special case where we use exactly the previous phrase, we know previous phrase was AN. We're in the special case that we need the same phrase again, so we append the first character of that same phrase. That's our new code word, or new phrase for the text. So we add that to the dictionary and also use it right away. All right. With the key things out of the way, so if you have questions about the decoding, maybe we should do that first. If not, I'd like you to think about a bit about the extreme cases for this. Oh, kicked me out again. Okay, slider keeps reloading. I'll get there eventually. Well, lots of thinking time for you this time. Okay, there we go. Mm-hmm. Okay, in the interest of everyone at home, I hope it's just Slido that's slow and not our connection here. I think we've been well over 30 before, so let's wait a little bit. I didn't reset the answer, so I don't know how many we've had today. But given that you had a lot of time to think while I was fighting with Slido, let's pretend 30 is enough. And that means one more. Oh, okay. There we go. Let me dissect a bit why that's the case. So this is a question, in a way, first of all, a text that consists of just A's repeated hopefully is something like the best case for compression. It's as boring as it can possibly get. So we should, in a way, see this as the best possible case. What's, in the extreme case, the compressibility, or what compression ratio can Lempel-Welch achieve if the text is as boring as can be. And so let's write a bunch of A's. Now let's start simulating what the Lempel-Welch algorithm would do to see if we can spot a pattern. Initially, it'll fill its table with all the symbols in the alphabet. Let's suppose whatever A is one of these, right? So the first step, the first phrase we find is just the single A. We encode the code word for that, whatever it is. And then we add A plus the next character to the dictionary. That's how it always worked. So we add AA to the dictionary. And then we move on. Next phrase is precisely that AA that we just created, right? That's the longest match we can find. We encode that and store that plus the next character to the dictionary, which is 3 A's. And then want to guess why what happens? We find the 3 A's right again. So the next phrase will be these. And then we add a 4th A, put that in the dictionary, which is again what we find. So you can probably spot the pattern by now. If you decode this, by the way, we will always run into the weird case where we use the phrase that we just are about to add. So if you want to practice that and see if you got the cases right, this is a simple example to force the special case. Okay, so we always make the phrases one longer. What does that mean for the number of phrases? If we sum up the total length that we cover with phrases, then let's open, this runs to something that we don't know, but we want that this covers at least the length of the string, right? So if you put some specific number, k, that we don't know yet, if that inequality is fulfilled, then we have enough phrases to cover the entire text. And so this sum is, in asymptotic notation, let's write it on this side, is k squared over 2. Now I know you can probably work this out. You all know Gauss's little formula and so on. You can solve it entirely, but the point is, if you solve for k, then roughly the order of growth is root n. So that's why we get that. It's not super intuitive. You need to really think about some concrete example to see why that happens. If you just think about the procedure and I would have told you root n is the best possible, it feels like, why? There's nothing squarish happening. It's only through this indirect route. All right. So that's all for Lempel Welch. Let's briefly wrap up what we've seen. So there's a few bits and bobs before I come to the pro and cons. There's a few things from the presentation where you should say, hold on a minute. I promised that we use this fixed size alphabet, say 12 bits, which means the dictionary is a finite size. If I keep encoding things, I will eventually fill up the entire dictionary. I always add one more phrase. So at some point, I have to deal with the situation that the dictionary is full. And there's different options what you can do. Each can make sense. Depends on what you want to achieve and what the input looks like. If you have reason to believe that the text is overall repeating, then it might make sense to just increment the code word size over time. The other option, often used in practice because it avoids running out of memory eventually, is to just flush the dictionary, start from scratch. So you fill it up, and then you pretend you start from the initial state again. And indeed, most applications of zip and so on, they have a special code word where the encoder can say, I think now is a smart time to just abandon the dictionary, flush it, and start from scratch. And why would you ever want to do that on purpose before it fills up? You would want to do that if the text changes its nature. So if there's, say, if it's two documents, one in English and one in French, concatenated, then maybe there's not too much repetition in the French part branching back to the English part. And if you can somehow, with some heuristic, detect, say, you've always just used single letters for a while, then maybe it's better to just flush and start from scratch. Things like that people try to do in practice. From our side, it's just, we'll mostly in our examples, we'll just treat the case where you still have time, still have space in your dictionary. For a general implementation, you have to just decide what you want to do. All of these have their pros and cons. So this gets better compression, but might fill up your main memory because you keep adding to a dictionary. This avoids that, but if you flush the dictionary too early, then you may miss some repetition from far back. All right. The good part is that encoding, decoding all runs in linear time. And if you have space for the dictionary, you can even do it in streaming mode. You don't ever look back into the text, really. All you need is your dictionary. And that's why people use Lempel methods also for transport layer compression. Now, good question. At which layer is this? I think it's at HTTP layer. So web traffic, you can automatically tell your operating system to compress the stream before it leaves the network, before it leaves on the network. And that this can be done while just reading the text once and outputting the compressed result. That's important for such an application. Okay. So we like the fast encoding and decoding, obviously, and that it works in this streaming way. It also works really well for many types of data that we seem to have in our world. And I've mentioned why before. It's just a lot is text-based in one form or another, and there's many human-friendly text tends to have small repeated parts that mean something to us. With a bounded dictionary, at least, if we do this flushing technique, we're somewhat local in the repetitions that we can catch. And even if you keep increasing your dictionary, you will be able to reach all the way back to find repetitions, but you make all code words one bit longer, which may not be a good deal in all cases. So then you can play more tricks like the first bullet. Take these code words that come out of that and try to compress that further with some other technique like a Huffman code. But if you keep stacking things up too high, it becomes tough to understand what's happening. So there's some slight negative part that capturing really long range repetitions doesn't usually work so well with Lempel Civ. I'm just mentioning this here because we'll come back to that question later. I want to summarize what we've seen so far because these are the traditional compression methods and the three most important ones we've seen. I don't necessarily want to read that out all again. It's basically repeating what I said on the discussion slides of the appropriate chapters. But as a little service to you, I summarized it. And there's a few comments on where it's used in what form. As I said before, none of these methods is used in isolation as the solution for everything. They're usually used in combination. And we'll come back to that as well.